I have you loud and clear.
Hello.
Hello.
Welcome. Science.
And that is to say,
Physics, medicine, nature,
or
Space. Time.
the brain,
Life.
The universe.
Hello and welcome. And this week it's back to school for most of the UK and also for us naked scientists here in the studio as we don our uniforms for a lesson in the science of education.
plus a new drug that could cure malaria with a single drop, and we find out what happened to the Ice Bucket Challenge. I'm Connie Orbach.
I'm Kat Arney and this is The Naked Scientists.
The Naked Scientists podcast is powered by ukfast.co.uk.
First up, this week the UK government pledged to ban the use of microbeads in cleaning products and cosmetics such as toothpaste and facial scrubs by 2017. Given that a single shower with a microbead gel can result in 100,000 plastic particles entering the ocean, the ban is aiming to reduce the amount of plastic in our seas. But what exactly are microbeads? What damage do they do? And will the ban really make a difference? I caught up with Richard Thompson, Professor of Marine Biology at Plymouth University, at the British Science Festival in Swansea, for some answers.
Well, microbeads are very small pieces of plastic. They're part of a wider problem, if you like, of small pieces of plastic in the environment. Pieces that are described as microplastic, and that captures any piece that's less than 5 millimetres or so in size. And we know that these really tiny parts are widely distributed in the ocean, that a wide range of creatures is ingesting them, and there's evidence from laboratory studies of harm. But it's important to understand that microbeads from cosmetics are just one source to this wider picture of microplastics.
What do we know about the kind of harms that they're causing and the kind of organisms that they're harming?
We know that a wide range of organisms will ingest microplastics, and that includes creatures with a range of different feeding strategies: filter feeders, deposit feeders, detritivores, fish, birds, invertebrates, and we've got that information from the natural environment. The evidence about harm largely comes from laboratory studies where there's evidence of physical disruption that's caused by ingesting these microscopic particles.
So it actually kind of stuffs them up or causes them physical problems?
What it seems to do is compromise their ability to put on weight, if you like, and we're not completely sure what the mechanism behind that is, but invertebrates in treatments with microplastics present didn't fare as well as those in terms of where the microplastics were absent in terms of putting on weight.
And what about evidence of larger animals that it's causing problems?
There's very little evidence of harm to larger creatures. We know that a wide range of creatures will ingest microplastic, including potentially some larger organisms, but the picture of harm with respect to larger organisms is just not clear.
The ban on these microbeads has been because of fears maybe they could get into the food chain and we could end up eating them. Is that a problem, or do we need more evidence for that?
My view is that at the moment there isn't a cause for concern from a point of view of human consumption of fish or shellfish. But let's not forget that plastics are persistent contaminants in the environment. The abundance of them is increasing. They're not going to degrade. So, if we were conducting this interview in 10 or 20 years' time and we carried on with business as usual with emissions of plastics to the ocean, that might be a different story in terms of the quantities that are in seafood. But at the moment, I don't perceive that as being the driver behind the ban. I think that the ban comes from two perspectives, really. One is, it's not clear to me or to others what the societal benefit is of trying to cleanse ourselves with millions of small particles of plastic. It seems to us an avoidable source of contamination. There are alternatives that can be used. And at the same time, there's considerable concern about the accumulation of plastic litter in the environment, and there's growing evidence about the harm that particularly small particles can cause. Now, we're still trying to understand that the full range, the full potential environmental impacts of very small particles, but if we've got an unnecessary source of contamination, it seems to me appropriate to think about legislation to reduce that.
Proportionally speaking, how big a problem are microbeads?
Microbeads are a relatively small contributor. Even the highest estimates suggest that they could be somewhere 1 to 4% of all of the litter entering the oceans. The reason we have that uncertainty is because we really don't have a clear picture of exactly how much litter is entering the oceans annually. We only have estimates. We know that in the UK, 680 tonnes of microbeads are used annually, and that's a reasonably precise figure that comes from industry. Now, that's a substantial quantity. It's considerably more than all of the litter that's collected on our beaches in voluntary cleanups by Marine Conservation Society. It's equivalent to 20 or 30 articulated lorries full of microscopic plastic beads. It's not a trivial amount. It's an amount that's worth us taking action about. But if we try to set that into context to the wider picture of litter, yes, microbeads are a small element. But to me, that highlights the scale of the problem that we face in terms of solving the overall picture. It's not a reason that we would not want to take action on unnecessary sources like microbeads. It sets the rest of the problem into context.
Richard Thompson from the Marine Biology and Ecology Research Centre at Plymouth University talking to me at the British Science Festival in Swansea last week.
Now, malaria is one of the world's biggest killers, with 214 million reported cases in 2015 alone. Unfortunately, things could get even worse, as the malaria parasite has developed resistance to all the standard anti-malarial drugs, making the need for new treatments ever greater. But things are looking up, as Eamon Comer and his colleagues at the Broad Institute at MIT and Harvard have discovered a whole new group of compounds which, as I found out, attack the parasite in a completely different way.
We developed a series of compounds that operates through a new mechanism of action which stops protein synthesis in the malaria parasite and eventually results in killing it.
So protein synthesis, that's kind of important to everything, right?
Absolutely, yeah. It's just a fundamental process. Once you shut that down, the parasite can't survive.
And how have you gone about looking for these compounds?
Efforts in anti-malarial drug discovery usually start by screening a collection of candidate small molecules for activity against the parasite. In our case, we imagined that anti-malarials with new mechanisms of action might be discovered using our unique collection of diversity-oriented synthesis, or DOS compounds. So these are compounds not typically represented in traditional pharmaceutical screening collections. They tend to be more complex and they have more three-dimensional features reminiscent of natural products. We also looked for compounds that appeared to work in all three stages of the parasite life cycle. And then finally, compounds most likely to have properties necessary to become anti-malarial drugs were prioritized.
You mentioned that this is important because it's combating the malaria parasite at every stage of the life cycle. Is that different to what we have now?
Yes. So the current anti-malarials typically only target the blood stage parasites. You could be receiving treatment for malaria but still be capable of transmitting the disease to other people. So drugs really are needed that target all stages of the malaria parasite to protect vulnerable populations and also to control the disease and prevent epidemics.
So where have you got to right now with this compound? What have you found that it can do? And you've done some animal trials, right?
Yes, so we're finding that certain members of this series provide a single-dose cure in animals. So this is significant because none of the standard of care antimalarials work in a single dose in these models. So, for instance, certain of the currently available antimalarials require 2 doses a day for, say, 3 days. So this is quite important in the field because you're dealing with resource-deficient areas. And so it helps with compliance if you can just administer a single dose rather than requiring multiple doses over multiple days.
I can see the headline now, 1 drop treatment to cure malaria. That sounds really exciting, but how long do you envision these next safety stages and clinical trial stages to happen before we can get this to a point where we're really getting it to the people that need it?
So it typically takes 12 years or so from initial hypothesis to registration. We hope to have compounds going into clinical trials within the next 4 years. But it all depends on how the safety assessment goes on these compounds.
It's a slow business you're in, isn't it?
Absolutely.
You mentioned that to look for this new mechanism of action, you went for a more complex type of molecule, which is, I'm guessing, harder to make. Does that mean that this drug's likely to be a lot more expensive than current antimalarials?
Not necessarily. I mean, one thing we're learning from our pharmaceutical partners is that one of the biggest factors in terms of cost is the dose of the drug. So, if we can come up with a compound that requires just one dose, then that's a major factor in terms of cost. But also, we actually think that we can come up with ways of making these very efficiently and competitive to traditional antimalarials.
Eamon Comer, and his work was published in Nature this week.
This is The Naked Scientists with Kat Arney and Connie Orbach. If you'd like to get in touch, you can email chris@nakedscientist.com, tweet us @nakedscientists, or find us on Facebook.
Still to come, there's more to giraffes than meets the eye. And how much of your academic record can you blame on your parents? But before that, it's time for our regular myth conception. And this week, Kat's been looking into a painful problem.
I'm sure it's something that most, if not all of us, have experienced at some point. That awful throbbing pain that comes with a headache, a toothache, or even just a bad knock, a trapped finger, a nasty cut, or another injury. Thud, 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 ow. It's often assumed that this is such a regular pulse-like throbbing that it must be linked to the heartbeat. It certainly makes sense that there might be pulsations of blood flowing through an injured or sore area, beating against sensitised nerves and creating that horrible throb. But although it's a logical assumption, dating back as far as the Greek philosopher and scientist Aristotle, it's a wrong one. Dr. Andrew Ahn and his colleagues at the University of Florida managed to disprove the idea that throbbing pain is linked to the heartbeat with an incredibly simple experiment. They simply found people suffering from throbbing pain, monitored their pulse rates and the pattern of the throbs, and compared the two. And they just don't match up. Ahn's team have actually published 2 papers looking at the relationship between throbbing pain and the heartbeat. One with people suffering from migraines and the other with people with severe toothache. One can only imagine how generous these volunteers must be to even want to take part in research while suffering such agonising pain. What they did was very simple. They just measured each person's pulse while asking them to tap out the rhythm of their pain throbs on a computer or a table. For the migraineurs, their heads throbbed at an average of around 62 beats per minute, while their heart rates were an average of 80 beats per minute. Even for people who had fairly similar heartbeats and pain pulses, they fell in and out of sync, suggesting they aren't linked. Similarly, for the people with tooth pain, their average heart rate was 72 beats per minute, while the average throb rate was just 44. Yet when the researchers looked closely, the throbbing clearly had its own rhythm. So if it's not caused by the pulse of blood, it must be caused by something else. But what? Using a technique called electroencephalography, or EEG, which is a way of measuring electrical activity in the brain, Ahn found that the throbbing correlated with a particular pattern of brain waves called alpha waves, which run through the brain at between 7.5 and 12.5 cycles per second. It's not clear exactly what alpha waves do, but the discovery that they might be linked to throbbing pain is an intriguing one. Although it might seem like a simple experiment, proving that the pulsing of blood through a site of pain isn't responsible for the throbbing is an important observation. Some medical professionals still use the presence of throbbing as a proxy for an injury or damaged tooth still having a blood supply, when in fact it may not be the case at all and could be misleading. And as anyone who's suffered from severe pain will know, the current arsenal of painkillers don't always work that well and can have side effects, including addiction. So discovering that the throbbing is linked to certain brain waves could one day lead to entirely new ways to tackle pain. Now that is a real brainwave.
Exciting stuff. And if you've come across any unlikely sounding science, then send it in to chris@nakedscientist.com. Now, it has long been thought that there's only one species of giraffe. However, a recent study of the animal's genes has concluded that there are, in actual fact, 4 different species. The discovery was made by Axel Janker and his team at the Senckenberg Society, Goethe University, who worked with the Giraffe Conservation Foundation to study giraffes from across Africa. Laura Brooks caught up with Axel to find out more.
There's very little research on giraffe. We're among the first to make genetic studies. Yeah, they have simply been overlooked by science, describing them originally as one species, and everybody was happy with that and stuck to it. And we, for the first time, looked much more closer at it and found these 4 different species.
I see. You'd think with them being the tallest mammal that they would be the ones doing the overlooking, but in fact we've overlooked them, it seems.
That's absolutely right. It is surprising that so little research done on giraffe, which is an iconic species for Africa.
Yeah. What does a species mean to you? So when I was at school, I was told that a species is a group of animals that can interbreed. But I've since learned that actually the definition of species is a bit more subtle than that. So what does species mean to you in your research?
The definition is very similar to what you have learned. It's a group of animals that can interbreed in nature. And obviously, these 4 species of giraffe don't do it. We don't know the reason why, but we don't see gene flow between these species. These 4 species are genetically distinct, so something prevents them from interbreeding in nature. They can interbreed in captivities, in zoos, and they do so, and they have viable and fertile offspring. But again, in nature, for some reason, they don't do it.
And you say that their genes are distinctly different. How different are they?
They're different enough to call them species, but if you want to have a comparison, they're as different as, for example, the genes between polar bear and brown bear.
Wow, well, that's quite surprising, isn't it? Because they look very similar, isn't that right?
That's right. They are not as distinct as polar and brown bear, where we immediately see we have different species here. But if you look closely, you see very distinct differences between the coat pattern. The reticulated giraffe has very straight lines around the brown fur region, while the Maasai giraffe, the lines of these brown spots is very jagged, and the spots are much more darker. And so there are more differences also between these different species if you know where to look.
And what do we know about how these different species came about? Is it simply that the different groups were geographically isolated from each other?
That's an excellent question. We don't know. And this is the exciting and fascinating part of the story, which we'll be studying now. We find them to be distinct, but we have no idea how they became extinct. It can be behavior, it can be geographic separations, there can be other things. We don't know.
Now, giraffes are endangered animals, aren't they? In terms of conservation, what are the implications of this discovery?
The implications are huge because giraffe has been seen as a single species. Now we have 4 species, and some of these species have only numbers of 5,000 or 8,000 individuals, and so they need to be protected. And now the Giraffe Conservation Foundation has the science to address African governments, to address conservation organizations, to convince them that giraffe needs to be protected.
So presumably they'll be looking at targeting conservation efforts at these 4, as we now understand, distinct species.
Yeah, that's right.
That was Axel Janker, and the study was published in the journal Current Biology.
Next, naked scientist Greer Jackson is dunking her head in cold water, all in the aid of science.
Remember the ice bucket challenge? I certainly do. My dad nominated me. I did it on holiday in Barcelona. The only thing we could find to put the water in, though, was this massive pottery urn. It seemed like a really good idea at 2 a.m. nonetheless.
It's so heavy.
Fortunately, though, my brother was on hand to do the pouring. And my dad was there to laugh.
Charlie Jackson.
And do you remember what it was in aid of? A really debilitating condition called motor neuron disease, also known as amyotrophic lateral sclerosis, or ALS in America. Although not a lot is known about the disease, we do know that it affects nerve cells in the brain and spinal cord that control movement. So as the disease progresses, you become increasingly unable to move, to talk, to breathe, whilst maintaining all your cognitive functions. It's something my dad knows a bit about because one of his best friends, Doug, died from motor neuron disease.
Well, we were at Manchester University. In fact, we teamed up at the end of the first year and moved into a house, so there were 7 of us at that stage. He stood out, actually. So whereas we were perhaps your more typical students in terms of our interest in beer and the like, Doug was a man who preferred gin and tonic. So we were a pretty close-knit group, in fact. And I suppose, it was around about 2007 when it became clear, or rather Doug, I should say, he had started to notice a certain slurring in his speech. He was referred to a specialist, and he simply said he had an illness called motor neurons disease. And we realised that we were living on borrowed time. And sure enough, over the course of the following 3.5 years, I think it was, he gradually became more and more disabled, and certainly for the last 2 years was in a wheelchair. And then around about that time started to completely lose his power of speech. And within a few months of that, he was reduced to more or less being totally immobilized, in fact. He bore it with fantastic fortitude and genuine good humour right to the end. And the end was he inevitably fell ill of some other, in fact, in this case, it was some kind of twisted gut problem, but he was too weak. And that was really the last that we saw of him. He used to have a great collection of very wild coloured socks. In his will, we were left 1 pair of socks each. We were the pallbearers at the funeral service. And so we were requested to wear these coloured socks. And in fact, ever since, we have carried on having our Christmas lunches. So now, in his memory, we attend those lunches wearing in my case, the bright green stripy socks that I was left. And in fact, we always order a gin and tonic that we leave in the middle of the table in memory of him, obviously. And to be honest, after it's warmed up and it's thoroughly not very nice, then we end up drinking it. But we try and remember him as best we can. And he was a wonderful guy who left behind a very young family, rather tragically. And so far as illnesses go, and my experience of illness is probably one of the worst things I've ever seen in that sense. So the Ice Bucket Challenge and any money that's ever raised to that end is very well spent.
The Ice Bucket Challenge raised more than $100 million, but that was over a year ago. So what's come of that money? Well, scientists like Ashley Jones were funded with the proceeds, and they've discovered a slight variation in a gene. It's called NEC1.
So NEC1 is multifunctional. There are 3 functions which are related to motor neuron disease. One is the development of cilia. It's also involved in the regulation of the membranes of mitochondria and involved in DNA repair.
So can I sort of think of it as a bit like the damage response unit of a cell, basically? If something goes wrong, it's there to repair.
Yes, very much. So it's regulation, keeping things in order, and also if something goes wrong, then it helps step in. So in a subgroup of motor neuron disease patients, there are small mutations within NEC1.
You can think of a mutation as an error in the code that creates you, but sequencing thousands of these genes to find these errors is a pricey business. And it was only made possible because of
things like the Ice Bucket Challenge. So we can extract genomes from tens of thousands of people who suffer from motor neuron disease and comparing their genomes with tens of thousands of those who do not suffer. And we've seen in NEC1 that there is an increased number of very rare but damaging mutations within this gene, which collectively contribute to motor neuron disease itself.
And so was this found in all people who have motor neurons disease?
So no, so it's found in a subportion. It'll be around 3%.
That's not very many.
On the face of it, no, it's not. But actually, what tends to happen with discoveries of when genes associate or we found a genetic mutation, we're able then to look at similar genes that have similar function with NEC1, or genes that interact with NEC1. And what we tend to find is that these are also dysregulated. Sometimes we find mutations in these genes as well. So really, NEC1 is about shining a light upon a pathway or a function that's going wrong in the cell.
Because really, correct me if I'm wrong, with things like motor neurons, we really don't have any idea about how it's caused, how it progresses, and therefore treatment's really hard to pin down if you don't know any of these biological pathways.
Absolutely. And another thing to add to that, years down the line, we don't necessarily have to explain 100% of the genetic causation of motor neuron disease. We just need to know enough to make an effective therapy.
And this is, I suppose, step one in that effective therapy. Do you think this would have been possible without the ice bucket challenge?
It would have been possible, but it would have slowed it down. Gathering tens of thousands of genomes is very expensive, and having that resource there has been paramount.
Dr. Ashley Jones from King's College London, and before him, David Jackson. That study was published in the journal Nature Genetics.
This is The Naked Scientist. I'm Connie Orbach and she's Kat Arney.
And now we're moving on to the main part of the show. And this week, it's all about education. When moulding the bright minds of tomorrow, what's the best way to do it? But Connie, it's not just the new school year or the announcement of grammar schools here in the UK that's got us thinking about this subject, is it?
That's right. It's actually something I read back in July. You see, every Monday in the Naked Scientist office, we take a look through the week's news. And on one particular week, something caught my eye. That was 2 pieces of research in 2 good journals saying essentially the opposite thing about how to educate children. And, well, I guess that intrigued me. How do we decide the best way to teach our children? And what's the science behind it? So this week, that's what we're going to find out. But first, back to those papers.
I am Susana Claro. I am currently a doctoral student at Stanford University, researching about beliefs that influence your motivation in academic setting mostly. Growth mindset refers to the implicit beliefs people have about the nature of the intelligence. Carol Dweck has been studying this for more than 20 years, and she distinguished 2 extremes on how these beliefs about your intelligence could be. In one side, she distinguished fixed mindset people for people who believed that intelligence is something fixed, is something you inherited or doesn't change over time. And the other extreme, she labeled as growth mindset, those people who have this belief that intelligence is something malleable, that changes over time and can grow, basically. And these 2 mindsets makes you face failure and interpret failure in radically different ways. And therefore, they trigger different types of action that in the long term can stop your learning or can instead spur it and lead you to new challenges and new learnings.
Do you think your abilities are set in stone? Or are they malleable and open to change with a bit of hard work? Research from the States has suggested that those with a growth mindset, the belief in power over your own destiny, achieve more. And Susanna's work has built on this with the biggest sample size yet, 200,000 Chilean students, looking at educational achievement and economic background.
We weren't expecting to find such a strong relationship between family income and mindset. And we find that as you go up in the family income line, the proportion of students with a growth mindset goes higher. And this is very worrisome given all we know about the benefits of having a growth mindset, especially for academic achievement. So it's a big call of attention that we have to address. We have to help students develop a growth mindset, especially in those sectors where it's more scarce. We find also that mindset predicts achievement at every income level, at every school. Virtually every school have a positive relationship between mindset and achievement. That means that even after you control for every characteristics we have of student background and school background, if you found two students that have everything similar but different mindset, the student with a growth mindset will have a better score than the student with a fixed mindset.
According to Susanna, the mindset of a child impacts on how much they achieve, and it's important that they believe that intelligence is not set in stone. But is mindset really all we need to win big?
Something on the order of 2/3 of the differences between children in their GCSE scores can be accounted for by inherited DNA differences.
2/3. A big number, right? That's Robert Plomin from King's College London, and those results came from a study of twins that Robert did a while ago. He has now built on that work to look at unrelated individuals using only their DNA.
And we find that we can account for 9% of the differences between children in GCSE scores solely on the basis of their DNA differences.
Now, I know what you're thinking. That sounds like a lot less than 65%. But the thing about this new study is it only looks at a tiny proportion of the whole DNA. And as more is explored, it's likely that this number will rise. And when you think about what these numbers mean in real life, well, it's quite staggering, as the difference in that 9% of intelligence can make up a whole GCSE grade. So clearly these numbers are important. But thinking about Susanna's work, knowing the limits of your intelligence sounds pretty damaging. Robert, however, sees it a different way.
It doesn't mean we're deterministic about it. It doesn't mean you can't do anything about it. But what it does mean is that it's much more difficult for some children to do well at the academic game. Other kids will find it kind of easy to do. Now, if a child is at the low end of that distribution, I think it's useful to know that. Because you can, first of all, adjust expectations if that's what you want to do. If you just assume as a university professor your kids go on to be university professors, it's not true for all of your kids because there's a big distribution genetically within a family. And so if you say, okay, this particular child had a low polygenic score, it doesn't mean you give up on the child. It just means that you're going to have to roll up your sleeves and work a lot harder. It's going to be more difficult. You've got to recognize, though, that kids differ genetically. It's not just a matter of saying, well, get a good attitude and work really hard. For some kids, they can work as hard as they want and they can have the best attitude in the world, but it doesn't mean that they're going to excel at academics. So I think the thrust of this is to say we need to individualize learning. We don't have a universal national curriculum where we expect one size to fit all, because it doesn't, because kids are so different genetically. It can be a positive message to say that certain kids are going to need a lot more help and resources.
So as often happens with these nature-nurture debates, it seems for Robert it's the interplay that's important. But what about Susanna? Does knowledge of limitations fit with growth mindset?
People worry that you can't tell them the truth. Like you can't, especially the all this self-esteem movement that you have to make the child feel better. And this is important. It's important that the child feels that he's worth, because everyone is worth no matter what. So that message was confused by saying that everyone was okay and they weren't failing in anything. And that is a wrong thing. We have to, the message I prefer is the truth with hope. And there are studies that show that when you tell the student, yes, you need to grow on this, but I know you can do it, and I'm saying this because you are able to do it, because I trust you will be able to do it, that shows much higher rate of response or rewriting an essay and after all growing than when you either just tell the truth without the hope or you just don't say anything, right? So tell them where they are, but tell them that can change. That's not destiny, and they can grow their brain. Their connections are going to get faster, they're going to get better, and you trust that they are going to do it as well.
A good message there. Susanna Claro from Stanford University, and before her, King's College London's Robert Plomin. Now, Connie, did that clear things up for you?
Yes, yeah, it really did. And I can see how the two ideas can exist together. But it's also true that they're both pretty controversial areas of research, so I don't think anyone has really worked it all out yet. Now, Kat, before we move on to the next part of the show, I've got a little pop quiz for you.
Oh, God.
We're going to check up on your GCSE science.
No!
So this is from an exam paper you would sit at age 16.
Oh, my God. OK, hit me.
I've just got a couple of questions.
OK.
And they're none of them. So sometimes you have to work out formulas and things, and they're just the kind of one answer things. OK,
Yeah.
So first up, this is a biology exam.
Mm-hmm.
Which temperature would be most suitable for growing bacteria in industrial conditions?
OK.
Your possible selection, 25 degrees Celsius, 40 degrees Celsius, or 100 degrees Celsius.
Ooh, I would go for 40.
Very good, very good. And I guess the human body is at, 37 degrees?
Yeah.
So that must be a good place for it.
Somewhere around there?
Yeah. OK, you're doing well so far. So I've got one more for you.
Uh-huh.
Complete the sentence. The atomic number of an atom is...
Oh, God. Is it? It's the number of protons, isn't it?
Yeah,
Oh.
yes.
This is awful.
Ding, ding, ding. You did well, though. You'd clearly be OK taking your GCSEs today. But of course, not everyone finds exams that easy.
That is right. I do have a little bit of an advantage, particularly with the biology, because working here on The Naked Scientist, do my own Naked Genetics podcast too. I'm down with the genetics, not so hot on the physics. But when it comes to exams, who decides what needs to be tested and how does that happen? Stephen Diston is the head of the science subject team at OCR, a UK exam board, and he's here to talk us through the process. So, Stephen, who decides what goes on that exam paper that gets slapped on the kid's desk at the end of term?
Well, the exam paper will be written by a group of people who clearly they've got expertise in that subject area. They'll also have experience of teaching students in that age range. But they're constrained as to the areas they can test on the examination by the content that's laid out in the specification. And that document is set to a certain degree by the government, who will indicate the content that they expect to see in each of the individual subjects. And for some subjects, the entire content is laid out by the government. In others, you might get 50, 60% of the content is mandated. And then the exam board and the examiners have the freedom to select which additional content they'd like to put in there themselves.
So what does make a good assessment for kids? A lot is made of exams, but there's things like coursework, practical exams as well. What's the best way of figuring out how to test a child's knowledge and ability?
Well, with examinations, you're always weighing up some competing requirements. One of the big worries with the high-stakes exams, such as GCSEs and A-levels, is that there is always the possibility that people might be looking to cheat or to game the system in some way. So a high degree of security around the examination is part of what we're looking for. And that straight away tends to put some limitations on. An examination, it's far easier to control the security of that examination than something like coursework, where it has to be carried out under much less secure conditions. And of course, it may well be that the school needs to arrange equipment and resources weeks, even months in advance of the exam taking place. That being said, there's limits to what you can actually assess through an examination. And so if you look at practical science skills, the only way to really know if a student can put together the equipment and carry out a titration is for someone, generally the teacher, to actually watch them carry out the experiment and then assess how well they've done that. So there's always been a balance to be achieved between how much of the examination or how much of the weighting of the assessment is given to practical activities and how much is determined by exams. But from a security point of view, as I said, if you can examine it, you should examine it, is the current approach that's taken.
Well, that's from a security perspective, but I may be showing my age a little bit here, but I was one of the earlier years to do GCSEs, and a whole part of the GCSEs was it's this coursework element, and different exams have different proportions of coursework, and I understand now things like A-levels and AS levels here in the UK have more elements of coursework. Is coursework a good idea in terms of assessing pupils, and is that kind of swinging back towards no, exams are best?
Coursework is a very different way of assessing pupils because, if nothing else, you can allow a much longer period of time for students to actually carry out the coursework. That lets you tackle much more substantial pieces of work than you can do in an examination where it needs to be completed within a few hours and is unseen material. So it widens the scope for the skills that you can actually assess in coursework.
And kind of in my view, it's almost a more life beneficial skill. You know, when I do my job as a writer or broadcaster, I'm not turning up and sitting a 2-hour exam every week. I'm getting sources, I'm pulling documents together, I'm writing things. Is coursework a better way of testing those kind of skills that kids actually need?
I think it's an important way of testing those skills. It's not necessarily the only way you can do it. But when you look at the range of qualifications out there, as you look at qualifications which have a more vocational design and they're more closely targeted on particular career pathways, you see that the weighting that's given to coursework increases quite significantly. And there's plenty of qualifications out there which might be as much as 75% coursework and only a quarter of it based upon an examination.
But more broadly in the sort of the academic subjects, exams are still seen as the best?
They're seen as the most secure and reliable way of assessing skills in students. One of the changes that's coming through into A-level sciences at the moment is the decision's been made to actually separate out the practical skills from the examined results. So you'll get a grade in the future that's based purely on the exam. You'll get a separate result that actually says how you did on the practical skills element.
And I guess when we're training the scientists of the future, those are two equally important skills to be measured.
They are indeed, and for universities who arguably are the main consumers of A-level results, it really does make a difference to know whether the students that you're looking at, they may have a very strong theoretical ability within the subject, but actually is it safe to let them loose in the laboratory when they arrive?
A terrifying thought. And I've got one more question, which is a sort of a little bit of a sting in the tail, is every year we hear the exam results come out and more people are getting better and better grades and things like that, and people go, oh, they're easier now than they used to be in my day. Is that kind of really true, or are they just different?
They are indeed very different from how they were years ago. And, I mean, how long have we got to talk about this? We operate a particular system within the United Kingdom where it's not strictly what's called a norm reference system, so you have a fixed proportion of students who get the grades each time, but there is an element of comparing performance between students year on year against previous exam papers. So whilst you do have a lot of statistical analysis that goes into the results, you actually have experienced examiners, human beings, sat down looking at scripts that students wrote last year, looking at the scripts that students wrote this year, and making value judgments about the relative difficulty of the exams that have been sat, and looking for performance from the students that they feel matches the level of performance that was seen for an A or a grade C, whatever it might be, in previous years.
So I think that young folk, even if they don't have good knowledge of 80s and 90s pop music, it's not that their exams are a lot easier.
No, it's not.
Thank you very much. That's Stephen Diston from OCR.
This is The Naked Scientists with me, Connie Orbach, and Kat Arney. If you'd like to get in touch, then you can by tweeting us at Naked Scientists or emailing chris@nakedscientist.com.
Still to come, where is the research in education?
But first, Kat, I've got a couple more exam questions for you. Just
Okay.
2 more, I promise.
Okay.
So another chemistry one. The mass number of an atom is...
Oh, that's protons plus neutrons.
Yes, yeah, you've got your atoms down.
Yeah.
And one final one. Noble gases are in which group in the periodic table?
Oh, right. They're definitely way over the right-hand side. I know they're the furthest right because they've got no spare electrons for doing any reactions with. I want to... The number is there's 8 columns, so presumably they must be 8, I think.
Actually, they're group 0.
Oh.
And
okay, maybe it's changed since.
well, luckily we have an exam maker and a science teacher in the studio. So maybe, Stephen, you can explain what's happened there.
Group 8 is probably showing your age slightly because it is the 8th group as you work your way across the periodic table. But it's known as group 0 because, as you've correctly said, there are no free electrons in the outer shells for the noble gases.
So, I mean, I've got the principle right.
We'd have given you benefit of the doubt if you'd put that on your exam paper.
That's like a trick question.
Yeah, I think it's a trick question.
Well, there would have been a periodic table on the back of the exam paper, so if you'd taken a moment to turn it over and look...
I memorised mine. Clearly, chemistry is a very complicated subject, and education is clearly also a complicated subject. As we heard earlier, there are lots of potentially conflicting theories. So how much scientific research actually gets into education policy? David James is a sociologist and researcher in education at Cardiff University. So, David, basically the big question is there research supporting the way that children are taught?
There is. For a moment there, I thought you were going to ask me a science question, and I was getting nervous.
Right.
Yes, there is. I mean, there's an awful lot of educational research, perhaps not as much as we need. In the 5 years up to 2014, the Research Excellence Framework process that looks at the quality of education research recorded about £290 million worth of research in the education field in that 5-year period. That actually sounds like a great deal of money. It's not that much if you compare it to some branches of engineering or even actually psychology and neuroscience. But it's still sizable. And that includes a lot of studies that are done by academics, sometimes academics working directly with teachers and sometimes working directly with policymakers. And some of that research does have direct impact. You know, a good example might be a piece of work by Oakhill and Kane on the teaching of reading. But there are many, many examples of work that does find its way through into legislation, into the curriculum, and into classrooms as well.
But what about the kind of ways that children are taught now? I mean, is everything that a kid will go through at school, is that based on evidence?
Definitely not. It's understandable that it's not based on evidence. You know, we have a long tradition of schooling. If you think about where schools started, think why we have the subjects we do have at GCSE. It's not because someone's, done a thoroughgoing study and decided that's what we need. It's partly because that's what went into the pre-grammar school curriculum a few hundred years ago. So there's an awful lot of tradition, there's an awful lot of joint professional assumptions, many of which are useful and many of which, have on a daily basis prove their worth.
But then what sort of sciences are now feeding in to educational policy? I mean, you've mentioned psychology, but what sort of scientific research does go into education?
Well, that's a really good question because it's a pretty broad field. Education is an interdisciplinary subject, if you like. It draws on disciplines like philosophy, sociology, economics, psychology, social policy, political science, all sorts of things get into the mix in different studies, and that's seen as a good thing. I think the point I would make about it, though, is that there is a problem with the way in which the big issues in education are conceived very often, and they're seen as sort of amenable to amelioration through work with individuals or with individual learners, when often they're actually system problems. They're much bigger.
These problems are really big that need addressing
really
through research.
Yeah.
And so say there are things that research throws up and says, oh, actually, this would be a really good idea if we started doing X like this. How do you get that information to teachers, to policymakers? I mean, what's the sort of the flow like from the research to the actual people on the ground?
Yeah, it could be a lot better. There was a spell in the 1980s when some in policy circles were blaming educational researchers for not working hard enough to do that. I think that's now seen as both a thing that's been resolved and to have been a bit politically motivated at the time as well. There's these days also a perception that policymakers might take more notice of research than they do. And there's some really good examples of that. I mean, a good example of a system problem would be some recent research on the children starting school. And many parents will know, that if you're born in August, you might be up to a year younger than your classmates when you start school. Now, that difference traces right through to GCSE. There's actually a really significant difference in the net or average achievement at GCSE from those children who are younger in the class compared to the older children. That's really robust research. It's based on millions of cases. It uses very advanced statistical techniques. It's really robust and rigorous.
We've talked about the kind of research from fields like psychiatry and sociology feeding into education and educational policy. What about some of the, I guess you could call them the harder sciences? I'm thinking things like neuroscience, the real studies of the brain. Have they got benefit for how we teach our kids?
Well, they could have, but I think a lot of the excitement isn't really warranted. The best way to explain that is to give some examples of what the really big questions are that face the education endeavour as a whole at the moment. Things like the persistent educational inequality and the relationship between people's backgrounds, socioeconomic backgrounds and so on, and the attainments that they end up with. That's a really persistent thing, and it's got many facets to it. If you take, I can just list a couple of others quickly, how, for example, specific public examinations that you've been talking about earlier in the programme, GCSEs, are not just used to measure attainment on the part of the individual student, but they become this currency for measuring teachers and schools and head teachers and all sorts of other things. In fact, to such a degree that at times it's almost absurd, the reliance on those for comparing schools. Both of those problems are actually not amenable to much neuroscientific approach.
Yeah, you can't put people in a brain scanner and figure out income inequality.
No, indeed. And furthermore, the problem with that is that there is already a tendency to individualise problems like that. For example, you hear politicians talking about raising aspirations amongst disadvantaged young people. That's quite a regular thing that you hear. But actually, the research evidence shows there's no shortage of high aspirations across most disadvantaged young people. It's not about that.
People do want to do well.
Yeah, they do. And on the whole, they really do. It's not about aspirations. It's about the nature of the system in which they're caught. You can bring to bear all sorts of systematic and rigorous research processes to look at those systems and say things about them that might be useful and might lead to positive change. But the wrong place to look would be inside, as it were, inside the individual, or to look at brain function first and foremost, I would argue.
And is there anything that research has thrown up that you know of that would really make a difference that is just not being implemented? Is there sort of one thing it's like, if we could actually do this, this would make a difference?
A really good example of that is this research work on summer-born children. In this day and age of quite sophisticated data usage, it's really quite simple to use age-adjusted test scores instead of treating everyone in the same school year as if they were the same. It's really simple to do that. And what it would do is to, first of all, give those individuals a clearer picture of where they are. It would compare like with like, rather than comparing them with children who are much older or much younger than they are.
Clearly something that does need some work. Thank you, David James from Cardiff University, and thanks to all our other guests, Robert Plomin, Susanna Claro and Stephen Diston. And to round off the show, it's time for our question of the week, and this time Laura Brooks has been scrubbing up an answer to this clothy conundrum sent in by Kevin.
Why does line drying make clothes rough?
Everyone loves the feel of a soft, warm towel straight from the tumble dryer, but towels dried on a washing line can end up crunchy and stiff. Why does this happen? Holly on Facebook thinks too much soap could be to blame. Meanwhile, on our forum, Atomic S suggested that the movement from a tumble dryer would loosen up fibres, making them softer. To find out more, I contacted Neil Lant, Research Fellow in the Fabric and Home Care Division of Procter & Gamble, who make Lenore fabric softener.
Our fingertips alone have over 2,500 sensory receptors, and our brains are constantly interpreting how things feel, sometimes at a subconscious level. When we pull clothes off the line or out of the dryer, our brains are focused on the task at hand, and we immediately know whether our laundry feels stiff and rough or whether it feels soft and flexible. The feel or softness of a garment is impacted by the physical properties of smoothness, flexibility and fullness. These physical properties are affected by the original garment construction, the type of any finish used, the fibre type and of course how it's laundered. A fabric that's made from a tight weave with highly twisted yarns like a cotton terry towel has a fullness to it, because the rigid fibres can support the structure, whereas a fabric made from a knit is more elastic and has a springiness to it.
Cotton fibres are made of a natural polymer called cellulose, the same stuff we extract from wood pulp to make paper. The cellulose chains stick together by a process called hydrogen bonding, which makes the cotton fibres very strong. However, cellulose is also very good at absorbing water.
In the presence of large amounts of water, like in a washing machine, the fibres swell, hydrogen bonds between the polymer chains are disrupted, chains can slip past each other, and hydrogen bonds reform upon drying. When fabrics are line-dried, water drains and evaporates, causing increased cellulose-cellulose interactions between fibres and yarns driven by capillary attraction. As the fibres deswell, new hydrogen bonds are formed within and between the fibres. It's like setting the fabric in stone. Whereas when the drying happens with motion, as in a tumble dryer, there is less opportunity for these fibre-fibre adhesions to occur. A highly structured fabric like a terry towel has twisted yarns and loops, and when new hydrogen bonds are formed, the towel feels very harsh since it is rough and stiff right off the line.
Mystery solved. Thanks, Neil, Holly, and Atomic S. And next time, we'll be answering Josh's question.
Do animals ever experience the placebo effect?
What do you reckon? Can your dog tell the difference between a real pill and a fake one? Send us your answers to chris@nakedscientist.com, tweet @nakedscientists, or get involved on the forum, nakedscientist.com/forum.
And unfortunately, that's all we've got time for. Next week, we'll be unlocking the mysteries of the Milky Way as we examine some of the first findings from the Gaia space probe. The Naked Scientist comes to you from Cambridge University and is supported by the STFC, the EPSRC and Rolls-Royce. I'm Connie Orbach, she's Kat Arney, and until next time, goodbye.